Alright, for lab 7, what we're doing is we're using a Michelson Interferometer to measure the, to measure various indexes of refraction of materials. Before we can do that, though, we have to find a precise measurement of the wavelength of the light that we're using, which is a large laser. So, the basic premise is that light comes through here where half of it will reflect this way and half will go through this semi-transparent material here. And there it will be reflected back to this material where, again, some portion of it will be reflected back, but some portion of it will be going this way. And what happens is the portion that went this way and bounced back will have a different distance that it traveled than the portion that went this way and came back. And the distance is controlled by this knob here, which very, very slightly moves this reflective surface here. The idea is that the different path lengths mean that the light is at different points on its wavelength. So, depending on how far one is moved with respect to the other, you either have destructive interference, where it becomes 0, or constructive interference, where it doubles. And what it allows for is a diffraction ring that you can see that has bright bands and dark bands. And by counting the number of bands that go by as you move this, you can tell the reliance on the mirror distance here that has on the motion of the interference patterns. And from that you can do the necessary calculations to find the wavelength of the light, and then once that's known, the index of refraction of the materials through which the light is passing. Alright, so right now I'm reporting the number of fringes that changes on our diffraction pattern here as a function of the distance that this plate is moving, which you can tell by the reading on the micrometer here. You can see that the diffraction pattern is moving, and what I'm doing is I'm shifting it shifting it so I can watch 20 fringes kind of come into existence across the top there. And then once I've done that, what I'm doing is looking at the reading here, and that's telling me number of micrometers that this mirror right here has moved. And from that, we're able to calculate the wavelength of the light going through. So I'm going to zero back out now. There we are. And I'm going to do a measurement.
So the step you just did was 5, right?
Okay.
Yeah. So the next two are like basically calculations. I'm repeating for others. So we never.
20. Right. Looks like 0.0675. All right, for lab 7 part 2, we're supposed to measure, or supposedly we're supposed to measure the index of refraction of air. We're not 100% sure because the lab manual's not here for it. But pretty much what we did was we found this. It has nothing in it. It's just air. And when we rotate it, it doesn't change any of the light. So we're pretty sure the index of refraction of light should be none, and that's probably going to equate to 1 in the future. So after that, we moved on to glass, the index of refraction of glass. So we had a few different tricks to try and make this easier on ourselves. One, we made it longer. So between our human reaction and being poor and our nerves jumping all around, if we do make a little jump, it's not going to be as huge an effect. We can still maintain what we're counting. And then to also make life easier is we use this and rolled. So that's just to keep it so the less jumps we have, that means we can do this in one try instead of like 15 million. So, but nice thing, so with this, we're watching the fringes go by. And in this lab, we got to count from 0 degrees and rotate it from 0 all the way to 10. Something that we noticed in the lab is when we go from 0 to 1, it only moved 6 frames or 6 fringes, but when we went from 9 to 10, it moved 22. So we noticed that it's not a linear, or the fringes don't move linear. We're expecting it to be sine. We haven't done the calculations yet to see if that is true.